Hi everyone, this is Derek, and today we're going to talk about how to create a tree transformation-based specializer in Asp SEJITS. I'll talk about why this is useful in a minute. For now, let's go ahead and grab the sample that we're going to be using for the screencast. If you go in your Asp directory, grab the latest version of the code using git pull. Then you go under specializers. You're going to see ArrayMap. ArrayMap is like a fancy version of Array Doubler, and I'll show you how it works. I've already loaded the code here into PyCharm. So what ArrayMap does, so Array Doubler, if you recall from the last screencast, takes each element of an array and multiplies it by 2. And it was pretty easy for us to take that and generalize it to multiply it by any number that we wanted. What would be even more general, though, is if we could take an arbitrary arithmetic expression, like this 2 times x plus 5, and apply that to each element of the array. The way this is going to work is we have this object, ArrayMap example, which inherits from ArrayMap. ArrayMap is a class defined by our specializer. You can see it over here, class ArrayMap object. I'm going to go through the pure Python version just to show how it works. Now, I start by creating an instance of the ArrayMap example object. I create an array that I want to apply it to. Then I call the map method. The map method, inherited from its parent, ArrayMap, just goes through the array and it calls the operation method on each element of the array. So operation is declared by the subclass, and it takes its argument, multiplies it by 2, adds 5. So that's very simple. And then our resulting list looks like this: 7, 9, 11, 13. It did 2 times x plus 5 on each element. So now we want to do that exact same thing, except we want to do it in C++, so that it'll run very fast, even on very large lists. So we're going to stop debugging, and I'm going to first show you briefly the template. So our template this time around, this is our Mako template. It's written in C++. It has some holes in it, one for the number of items in the array. The list class in Boost Python lets you pass a Python list into a C++ function, and it makes it very easy to extract elements from it using normal indexing. And Boost Python also supplies this extract double, which says if the list element is a double, just go ahead and convert it into a C++ double. So that's what we do here. We assume they're all doubles. Then we apply our expression. Now this is going to get embedded by the specializer. It's going to be written in C++, and it's going to convert x into a new value based on x. Then we're going to assign that back into the array. In the previous screencast, we returned a new array. This is just a little bit easier to do in Boost Python. Now I'm going to walk through how this happens. We're going to run and debug. As before, we're going to create our ArrayMap example. We're going to create our array. This time we're going to call map using trees. We step into map using trees. There's a lot of stuff going on here, but I'll explain it a piece at a time. The first thing we do is we call asttools.parseMethod. This is just going to convert our operation function declared by the subclass into an abstract syntax tree, which is a data structure that represents that piece of code. Now you can see operation AST down here in the debugger. It has a lot of fields. It looks pretty complicated. So we've supplied an AST Explorer module based on PyGTK that's pretty easy to use if you want to get an easier visualization of what it looks like. I'll go ahead and do that. So there's a using statement at the top of the file here. I'll just uncomment it. It's in CodeGen. I'll do AST Explorer dot AST Explorer. I'm going to pass in operation AST. I'm going to restart the debugging. And just set a breakpoint right here for when it's done. Okay, it opened the window. Here it is. This is AST Explorer. We can see that our data structure, if we go visit our method, here's our method. It consists of a module at the top level. This is a object of class module. Under that, it has a body attribute, which contains a list of other node objects. In this case, a list of 1. It's a function def object. Here's the function def object. Inside that, it has properties for its arguments, for its body, and for its name, operation. We're going to open up the body and see a single statement, a return statement. Inside that is the value being returned as a property. If I just go ahead and open this up, the value being returned is a binary operation. It's adding a number on the right, which is 5. On the left is another binary operation. It's a multiplication. It has a 2. And on the right, it has the variable x. Now, we're going to want to get this value so that we can transform this part of the method into an equivalent C++ expression for our template. The simplest way to do that is to just, in the AST Explorer, right-click it, do Copy Expression. Then I'm going to visit my ArrayMap. I'm going to paste that in here. So it's going to be .body0, .body0, .value. And as you can see, that's what we already have here in the code. So that's going to extract the portion of the AST that we want. So now we have expression AST. That's the portion of the AST we want. And we're going to pass it to converter. So converter here is a subclass of asttools.convertAST. ConvertAST is the generic Python to C++ converter class that's supplied by Asp SEJITS. It has a visit method, and if you pass a Python AST to its visit method, you will get back an equivalent C++ AST. So the default converter only works on basic arithmetic expressions. It's sufficient for what we want to do here, but it's not able to handle arbitrary Python. That would be much more complicated. So we get expression CPP. Now we can use AST Explorer to see what this looks like. I'm just going to paste this down here, put expression CPP in its argument, restart. Here is our new AST Explorer. So C++ expressions in their toString method by default render as how they're going to look in C++. So our expression as a whole is going to look like this, 2 star x plus 5. If we open that up, we'll see it has left, op, and right attributes, just like the Python bin op node did. It has a left node, which is also a binary op. This is a number. This right has a name. This tree is a little bit simpler than the Python AST. That's just because the C++ AST class we use happens to be pretty simple. Now that we have our C++ expression, which we get from the toString method of this tree, we're just going to go ahead and embed that inside of our template in the expression location. That gets rendered into a template. And just like before in the template screencast, that gets turned into a C++ file, which gets compiled and executed at runtime. So from here, it's all stuff that you've already seen. We're compiling the C++ file, and we're done, and the tests have passed. Now we're going to look at how we can modify the AST converter to do something a little bit fancier than just the default functionality that's supplied by ConvertAST. So first of all, let's go ahead and open our tree that we're converting in AST Explorer so we can take a look at it. I'm just going to run that. You can see it has binop, and it has num nodes, and it has name nodes. So a simple thing that we could do is we could say each time that we see a binop node, if it's an add binop, we want to print out I saw an add, or if it's a multiply binop, we want to print I saw a multiply. So the way that we do that is we just define a method here, define visit binop. It gets passed the node, and the node has these properties, left, right, op, And we're going to take the op, and we're going to see if it is an add. Now the way that you test if something is of the type that you want is to use isInstance. And in this case, we've imported Python AST as just AST, so we're going to do ast.add, and we're going to print saw an add. And we can do the same thing for multiply. If our operation is a multiply, we can print saw multiply. Now, the visit binop function in the convertAST class is responsible for taking this binop node and converting it into an equivalent C++ node. And we still want to do that if we want our program to work. So we're going to want to call the superclass, and we can do that with just standard Python call super, convert self, visit binop on the same arguments. And I meant converter. There we go. Now if I go ahead and close this, run the program again, take a look at our console, close my AST Explorer, it'll say saw an add, it's all multiply. And the test still succeeded. So that was pretty simple. For the next part, you're going to have to participate. If you haven't already, go ahead and visit the code, get it open, and we're going to do exercise 1. In exercise 1, the goal is to modify converter to compute a running total of all the constants that it encounters. Then at the end, you want to print out that sum to the console. So for example, if you see 2 times x plus 5, it should print out 7. So it sees the 2, it sees the 5, it adds them together. Go ahead and pause the video at this point, and when you're ready to see the solution, unpause it. Okay, now we're going to continue with the solution to exercise 1. We're going to get rid of visit binop. If we run this and bring up our AST Explorer, this is going to pop up AST Explorer. Inside here, you see that numbers are of type num, and they have an attribute called n, which contains the number that we want to add. So we're going to define visit num, and then we're going to look at node.n, and we're going to have some kind of running total, self.sum, that is going to have node.n added to it. And of course, we still need to call our superclass. So that we still compute the right result. We need to initialize sum to 0. And finally, we need to print it out at the end. So down here, after we're done visiting, we can just print converter dot sum. Now I'm going to execute this. Close AST Explorer, and you can see it printed out the total 7, just as desired. So that was a fairly easy exercise. The important thing to remember here is that the AST Explorer will tell you what the node type is that you want to visit, and it'll also tell you the attributes that you can extract from that node. It's also very important, if you're using the default functionality of convertAST, to always call up to the parent class's version of the visit function. At this point, we're going to try out exercise 2. It's slightly more difficult, but it's more like something you would really do in a real application. So let's imagine for a minute that you're working with an architecture where you have a special multiply function that, in your circumstance, is faster than the normal multiply function. So you don't want to use the normal multiply. You want to replace it with a call to your multiply. Here's what you're going to do. Exercise 2. Modify converter to translate any multiplication into a call to a custom C++ function that's called myMultiply. So in your case, you can just make myMultiply multiply the two numbers together. That's fine. In a realistic case, it would do something more interesting than that. So if you see 2 times x plus 5, that should turn into the C++ expression my multiply 2, x plus 5. Now before I start you on this exercise, I'm going to quickly show you how you create C++ AST nodes. The easiest way to see that is to go visit convert AST node. Convert AST has a bunch of visitors in it, and each of them create a C++ AST node. This one's creating a C number node, this one's creating a string node, this one's creating a C name node, this one's creating a binop node, and so on. Sometimes it just emits strings. This is okay for things that either don't have a node or are very simple. For this exercise, you're going to want to look up the visit call method. And this will provide you a model of what you need to solve it. So this is exercise 2. Go ahead and pause the video and try it, and unpause the video when you are ready to see the solution. Okay, now we're going to continue with the solution of exercise 2. We're going to go back to our ArrayMap class, erase the stuff we were doing before. I'm going to bring up the AST Explorer so we can take a quick look. So it's a binop, and if it's a multiply, our binop is going to have its op attribute being of type ast.mult. So we did this before. We can just visit binop, and we can look at its op attribute. If it has the right type, we do some stuff. Otherwise, we just do whatever the superclass originally did. For the multiply, we want to make it call the function myMultiply. So we haven't actually created that function yet. It's going to look like this. It's going to return a double. It's going to do myMultiply. It's going to take 2 doubles as arguments. And it's just going to return x times y. Simple enough. So we want it to call this C++ function in the C++. And the way that we're going to do that, I hinted that you might want to look at this visit call method in AST tools. If you look down here on the last line, it does return call. It passes a name and then a list of arguments. So we're going to do that. We're going to return. So CPP AST here is going to be CPP, cpp.call, cpp.cname, and our function is called myMultiply. Now here you can see that for the arguments in AST tools, it's visiting each of the arguments in node.args and calling self.visit on them. And that's going to return an equivalent C++ tree for that argument. This is a recursive strategy. It's very common in any kind of translation that's based on tree transformations. We can do the same thing for our binary operation, visit node.left, visit node.right, and that will give us the 2 arguments that we want to pass to myMultiply. Now that we've done this, we should be able to just execute it. Need to get rid of this old code, and away we go. It compiles the code, it executes it, and the tests succeed. So if we want to see what that code actually looked like, we can just set a breakpoint here, and we can run up to this point and take a look at the rendered variable. If I go down to the watches, I look at rendered, copy value. I'm just going to paste this into my handy document here. So as you can see, it has myMultiply, and here it did myMultiply 2, x plus 5, as desired. That's all for tree transformations. Feel free to try and come up with some other interesting things that you can do using Converter. It's very simple to extend. Any kind of node that you want to visit, you can just visit that kind of node by adding a method, and you can create any kind of C++ object that you want. You might also want to look over AST tools and look at the existing visit methods on the default converter to get an idea of some of the interesting kind of tree transformations that you can do. There's also some other classes in here that do other tree transformations beyond what the default converter does. For example, a loop unroller class that unrolls a C++ loop into a fully unrolled C++ loop. And you can this one takes a C++ AST and emits another C++ AST. You can also take a look at how that works. That's all for this. Thanks for watching.